So, good afternoon, everyone, and welcome to this afternoon's session where there are going to be a number of panels discussing a number of topics, and this is the first panel, and it's on the future of climate. My name is Professor Meric Srokosz, and I'm pleased to welcome to the panel Dr. Sanchez-Franks, Dr. Adrian Martin, and Professor Simon Josey. So I'm going to ask them, the first question is to say a little bit about what they do in their research and how it's relevant to climate. Over to you, Ali.
Thanks, Meric. So I'm in the Marine Physics and Ocean Climate group. And the two areas of research that I'm looking at right now are the system of currents in the North Atlantic. And these are really important because of how they affect climate and weather in Western Europe. And the other area of interest that I'm looking at right now is the Indian Ocean and the South Asian monsoon. Now, how a lot of us know, the ocean absorbs most of the excess anthropogenic heat. And 25% of this heat is winding up in the Indian Ocean. And this has a really big impact on the South Asian monsoon system, which leads to a lot of different extreme events.
Okay, so I'm Adrian Martin. I'm in the Marine Systems Modelling Group here at NOC. And my interest is primarily in terms of the marine ecosystem, all of the animals in the sea, and particularly how they help the ocean take up and store carbon. And in answer to your question about the relevance to climate change, you know, if that carbon's not in the ocean, then it might well be back in the atmosphere. So that's the relevance there.
Thank you. Simon?
Okay, my name's Simon Josey. I'm in the modelling group as well. And my research is primarily directed at the boundary between the ocean and the atmosphere, the SE interface, and the energy which flows between the atmosphere and the ocean. And that's very important for climate because a lot of the excess heat that we're putting into the atmosphere goes into the ocean, about more than 90%. So I'm really concerned about how that process happens and how that then heat is redistributed in the ocean.
Great, thanks, guys. So my next question is, looking into the future, because we're talking about the future of climate, what do you think is the major problem that are going to affect the ocean going into the future? Perhaps we'll go the other order now, start with Simon.
Yeah, well, in terms of, there are many problems you could list. I think sea level rise is a huge issue, and we don't really understand how the ocean and the ice, the polar regions of the Earth, so in the Arctic and in the Southern Ocean, interact. And that could potentially lead to stronger sea level rise than we're expecting over the next century. So I'd see that as a big topic.
Carbon. The ocean has 50 times more carbon than the atmosphere. And so given the size of the ocean, that means for, I think, 3/4 of the ocean, of the world's surface, then the atmosphere is directly in contact with a huge reservoir of carbon. We know that climate change is affecting the ways in which the ocean stores carbon. You know, that's through temperature, it's through changes in the ocean circulation, it's in perturbations of the ecosystem. But we still don't really fully understand the impact of those processes. And in fact, we don't understand the magnitude of them and how that's then going to feed back on climate.
So can I just follow that up and say, you talk about carbon, but how does that link to carbon dioxide, which is what we normally talk about? Well,
carbon dioxide, because, you know, you have these two, the atmosphere and the ocean in contact. And so you have this free exchange of carbon between the two in forms of carbon dioxide. The carbon dioxide dissolves from the atmosphere into the ocean, and then it can either get moved deeper by the circulation, but it can also get taken up by the organisms converted into organic material. So the carbon gets stored in quite a variety of forms within the ocean.
Ali?
I think about things more in terms of an ocean observations background. And so if you think about, you know, some of the latest results that have come out of the IPCC report, a lot of it's about the predictions of what we think are going to happen from ocean circulation and warming. And so I come at it from the perspective of how good are our predictions? How much can we trust the models based on what we know from the observations? So to me, that's one of the most important things, which is where do we need more observations to ensure that we have the correct predictions?
So, and what's the answer to your own question? Where do we need more observations?
Right, deep ocean circulation. We have a really good idea now of what surface ocean circulation looks like. We have a lot of marine robots in the ocean, like the Argo Flow program, and this measures the top 2,000 meters of the ocean. We also have satellites. So we start to get a really good idea of what ocean physics looks like in the top 2,000 meters. However, we have very little of what's going on beneath those 2,000 meters. And we are only starting now to develop a deep Argo Flow program, which goes to 6,000 meters. That's going to completely revolutionize our understanding of deep ocean circulation.
That's great. So Simon, as someone who's interested in the air-sea interface, would you say there are more observations we require at the air interface? And so what are they?
Well, yeah, I would say that, but I would also say, if I was asked that question, I would also say the deep ocean, because that we really have no idea about at all. But there are regions of the global ocean where we know very little about this connection between the ocean and the atmosphere. So the Southern Ocean in particular, very poorly measured. It has been historically. There are probably more observations on parts of the surface of the moon than we have of really good high quality observations in the Southern Ocean. We've only really had 2 sites at which we've made fantastic observations in the last 20 years or so. So I would argue for more observations there.
And what does that entail?
And that entails a surface flux mooring. So if you think about a big buoy with lots of instruments on, so probably about 2 to 3 meters high, with instrument towers on that measuring the wind speed, the air temperature, the atmospheric humidity, the sea surface temperature. Those are the things you need in order to understand the exchange of heat between the ocean and the atmosphere.
Okay, thanks, Simon. Adrian, from a carbon perspective, what would you want to see in terms of more measurements?
Oh, crikey, what don't we want? So, starting point, the ocean surface, we're still some way from having, I would say, global annual estimates of the amount of carbon coming through the ocean surface and the atmosphere. I think that's a first order constraint. We're still not really have cracked that one. And then once it gets into the ocean, there are a whole range of processes. There are physical processes, the solubility of the carbon within the water. We're developing sensors for that, but we still have a relatively restricted picture. And when you get into the ecosystem, we're just touching it really. We've made quite a bit of progress in terms of how phytoplankton, the tiny plants, take up carbon and process it. But the further you move up the food chain, the bigger the organism, the greater our uncertainty. And so we're now starting to think about fish, and now fish move carbon. There are some estimates suggesting it's very large. We don't really know, but how you go about measuring that is still very much an open research question.
So we're on lots more measurements. That's a good thing. What other sort of things do we need to be doing, do you think, in terms of improving our understanding? If you take, I think one of you mentioned that the weather systems across the Atlantic and hit the UK. What sort of things do we need to do to improve our understanding of the impacts of these changes in the ocean?
Well, there are processes. So if you think about that particular aspect, so weather in the UK, we found out in the last few years that the ocean itself and the memory of the ocean can actually influence these weather events. So you can get a cold signal at the top of the ocean in the North Atlantic, and it can get sequestered below the top of the ocean. So it can disappear down in the summer and then reappear the following winter. That's something we've realized quite recently, and it has quite a big impact on storm tracks. So it can increase the storminess over the UK depending on whether this process is happening or not.
And is that happening or not?
And that, yes, we think it is happening. We think there are particular winters in the last 10, 20 years where we can see the ocean having a direct impact on what's happening in Europe in the winter. So we are studying that right now from perspective of new observations and model studies of that process.
Yeah, I can add something really quickly, which is it's only really been since 2014 that we've had a mooring system in that part of the ocean, which is in the subpolar North Atlantic, looking at those changes in the ocean. And that's been really fantastic and completely changed our perception of how some of the systems of currents that we look at work. But think about when that started, 2014. I mean, it's less than 10 years. We need so many more observations to even begin to understand what that decadal signal looks like and how that's going to how that's going to play into the models and the systems and how we predict that.
So how long do you think we need to observe for to be sure we understand what's going on?
Well, many decades.
Right. So I should be well retired before that happens. Excellent. Adrian, you talked about carbon and carbon dioxide coming into the ocean. There are other effects, aren't there, of carbon dioxide entering the ocean? Could you say a bit about that?
Yeah, I mean, it's not really my specialty, but the obvious one that people are aware of is acidification. In terms of changing the chemistry of the ocean, and obviously that has a major effect on, people are very familiar with from the perspective of things like corals, where it's been a major issue. But even in the deep ocean, there are some interesting potential ramifications. For example, there are types of phytoplankton which are susceptible to acidification. And because those phytoplankton may be important for how carbon is transmitted deep in the ocean, essentially when they die, they sink, then that may actually change one of the pathways by which the organic carbon is getting to the interior as well. So there are multiple aspects there that we need to consider.
So people have talked about trying to improve the capture of carbon dioxide from the atmosphere by adding iron. Do you want to comment a bit on that?
I thought this might come up. Yes, so for anybody who's not familiar with it, people have suggested that because the ocean ecosystem is so good at taking up carbon dioxide and turning it into other forms and then putting it deeper in the ocean where it's out of contact with the atmosphere, that we should try and boost that growth. We should try and fertilize the ocean. And there have been a number of high-profile experiments that have done that, and I'll tell you with varying results. I think the thing that we really don't understand yet is the consequence of doing that, in that we are deliberately perturbing a system which is already providing a very important function in terms of carbon. You know, without marine life, atmospheric carbon dioxide would be 50% higher. So it's already doing something very important, and I don't think we've necessarily got the science that allows us to make informed decisions yet on what happens if we actually start pushing it even further.
Okay, so people often talk about a climate crisis coming up, and we need to make changes. What would you say are the things that we've seen in the ocean that convince you that we're hitting a climate crisis? Well, we can start with that.
There's an overwhelming amount, really. But again, I'll speak to it from my perspective and the sort of things that I do. I look at ocean circulation and heat transports. And so, for example, one of the regions that I'm interested, which is the Indian Ocean and the South Asian monsoon, you know, we see these trends of over 1 degree Celsius just over the last 6 decades in the tropics. I mean, the seasonal variability of temperature in the tropics is about 2 degrees. So you're seeing an increase that's half the variability already in just 5 short decades. And what we're seeing alongside to that is a lot of changes in the atmospheric system. So for example, the monsoon system. We've recently been found, and it's been reported loads of times in the media, that there is now more and more extreme rainfall events. So I'm sure many people have seen that in the last decade, there's been a lot of extreme rainfall events. This means excess precipitation or drought, and these have been directly linked to these increases in heat. And even just one of these events is a cost of up to, some of them have been costed to $40 billion. The lives lost are in the thousands, and these are just one of them. Imagine now we are getting an increase in these events that's just on the rise. We don't understand them. We really can't predict them. And they're all very clearly linked to the ocean taking up excess anthropogenic heat.
Yeah, so it's an interesting question because, the marine ecosystem is so complex, then tracking the sort of the influence of climate change through that ecosystem can be actually very difficult and sometimes lead to sort of rather surprising results. So one example that springs to mind, there is a type of copepods, a small shrimp, called Calanus finmarchicus, which probably doesn't mean much to anybody, but it's noticeable because the changes in temperature in the ocean have actually driven it a long way north over the last sort of few decades. And you might think, okay, sort of one particular shrimp has moved, who cares? But the reason it's important is because it's actually a very important food source for fisheries on, for example, the east coast of the US. And so you start to have these small effects on things at the bottom of the food chain that then propagate through. And so I think that's just one example of the way in which marine ecosystems can amplify and modulate the climate signal that's going in.
And also, everybody's very familiar with the coral reef problem.
Well, the coral reef, yeah, absolutely.
And so things like the Great Barrier Reef, 25% disappeared or something like that. It's quite a large number.
Yes.
Yeah. Simon, any thoughts?
Yes, yeah, I think I'm going to move away from the tropics and actually go towards the poles and the Arctic, as I'm sure many of our audience are aware online and in the room. We've seen a massive sea ice decline in the Arctic in recent decades. I think in the most recent IPCC report, it was quantified as something like 40% reduction in the late summer sea ice. So that has a huge impact on the ecosystem there, but it also has an impact on the ability of the ocean to take up heat and actually modulate the climate. So most of the time, the poles act to reflect sunlight. Sunlight comes in, but the the snow and the ice cover reflects that sunlight back to space, a lot of it. Once you take the ice cover away, that heat can be absorbed by the ocean and accelerate the climate change. And in fact, the Arctic is warming at a much greater rate than the rest of the globe. There's clearly a crisis there.
And obviously that gets captured in the iconic images of the polar bear stuck on a small floe.
Yes, yeah, that image is often used. But you can also see, perhaps not so appealing, but if you look at just satellite images of the amount of ice which was there 30 years ago and is there now, it's quite shocking and horrifying in a way to see that. It's really changing rapidly, and it's projected that by most models are saying that by 2050 we will have a summer ice-free Arctic. There will be no ice there in the summer.
That would be an amazing change in the Arctic. I think I want to change direction slightly, and Ali's talked about being an observational oceanographer, so I suspect lots of people out there who might be listening won't know what that means. So what do you actually do for your job in practical terms?
Right, so observational oceanography is essentially how are we observing the ocean. So actually I've mentioned really briefly two systems now that we have. One is a system of moorings that is usually much more of a long-term system where you can imagine we might put in moorings into the ocean at a certain latitude and leave them there for several years to measure properties like temperature, salinity, pressure, or biogeochemical properties like oxygen and carbon. And then we also have marine robots. One of the ones that we use the most are Argo floats. Argo floats are basically profilers, these sort of cylindrical yellow things about yay high, weigh about 25 kilos. We've thrown them in the ocean. There's about 4,000 now covering the ocean surface. And what they do is they profile the ocean up to 2,000 meters. And they're Lagrangians, so they just move with the ocean currents. We have a different type of ocean robots, which is very similar to the Argo float. And these ones are like a version 2.0 because we can remotely operate them and tell them where we want them to go. So we combine the systems of moorings, we combine the marine robots, and we also use things like the data we get from research expeditions or satellite data to get a complete picture of what we think that the ocean is doing. And so that's in a nutshell, a large part of my job.
So do you think going to sea on ships is becoming redundant? You won't need to do that.
I don't, because first of all, you need to deploy the platforms from somewhere. Most of these things require ship operations. You have to be able to go out there to deploy the Argo floats or the gliders or to set up the moorings. They have aided us in decreasing our, let's say, dependency on how many times we have to go out to sea, but we still very much need the research expeditions.
And from a carbon point of view, are there any different observing techniques or new things that we are thinking about in terms of
Yeah, I think to some extent it's coverage. I mean, Simon's already mentioned the fact that we still lack a lot of data from really important places. The Southern Ocean is an absolute blank spot really in terms of what we know. So there's a dire need to improve our carbon observations in the Southern Ocean. There have been initiatives going on to the floats. The SOCOM initiative to get extra floats into the Southern Ocean, which has been important. But we're still a long way from being able to produce accurate maps of the carbon going into the ocean. And then below the surface, I think in terms of capturing sort of the inorganic side of chemistry, sort of acidification and the various carbon dioxide, there's good progress being made in terms of sensors on that. But as soon as you move into organisms, then it becomes much more difficult to do things remotely. And so there's still a very important role there for seagoing observationists to be able to collect samples.
Can I add actually really quickly, because I mentioned with the Argo float program, what I didn't say specifically, which ties in with what Adrian said, is that in large part, the system has been operating since 2004, but it's very largely physical. So we're looking at temperature, salinity, and pressure. And it's only now that the biogeochemical Argo floats and marine robots have really come into play. So just to tie in that there really isn't a lot of data on the biogeochemistry.
Excellent. Simon, did you want to add anything to that?
Yeah, well, I thought you were going to ask me about my career as well, and what I do. But
well, yes.
Well, I would say I think there's something very important to remember, that observations play a huge amount in what we do, but so do computer models. My career has seen me go from observations towards computer models, but always using both of those in tandem. And I think there's a huge amount of effort within this building in particular, as well as observationally, in developing complex computer models of the climate system and of the oceans. And these, over my career, have got higher and higher resolution. That means we can see smaller and smaller scale ocean features. So we now have models which have 10-kilometer resolution over the whole of the global ocean, which is incredibly important for representing things called eddies. So you think about when you stir your cup of coffee and you see little eddies in the milk as they swirl around. We have those in the ocean, and nobody really understands, I think, the significance of these features for climate change. Most of the climate models we have don't incorporate those eddies fully when they're making predictions out of 50-year timescales. So that's a really important part of our research, and many of my colleagues are working on that. And I'm not so much working on that, but I'm asking the question all the time: how well are our models performing? What can I learn from observations, which will enable me to test the models and thereby gain more confidence in what the models are doing?
So do you think the challenge with modelling is having higher resolution or having better processes in the model? There's a balance there somewhere?
There is a balance there. I think it's both. Both of those things are big challenges. For example, I heard a talk just the other week where a modelling study of the Labrador Sea. So the Labrador Sea sits between Greenland and Canada. It's an incredibly important region because it's where a lot of it's a region where the surface ocean waters sink all the way down to the bottom. Well, not quite to the bottom, but they sink through the water column. And accurately representing that requires models which are getting down to a 60th of a degree. So that's a few kilometers resolution. So we need better representation of that sort of process, the convective processes. That requires resolution and better understanding of the processes themselves, which in turn comes from the observations, of course.
Right. So one of the things that people, when I talk to people about climate change, that they're impacted by is things that happen on land. So, you know, if you have a drought or a flood or excessive rainfall, whatever, they say, oh, well, that must be to do with climate change. Are there extreme events that we can see in the ocean that would give us a similar sort of warning sign that things are changing?
Yeah, there's marine heat waves. And there's several people at the UNOC that are looking at that now. And essentially what that is just in very simple terms, you can see an anomalous warming event in the ocean. That might be, it's usually the 95th percentile higher than the background mean. So, but maybe it's about a 1 or 2 degrees. And it can last from a week to a few months, although some recent reports have said that they can last up to a year. And so that would be kind of the ocean counterpart to those events we see on land. But of course, it's all interlinked, and a lot of the anomalous events in the ocean are directly contributing to those systems that then lead to floods or droughts.
Crikey. Extreme events. I mean, I think following on from what Ali said, then there's been some evidence that ecosystems can respond to that sort of extreme warming or sort of localized warming in a way that essentially reorganizes the local ecosystem. There was a case in the Pacific. The difficulty there is being able to attribute the cause, I think, as in a lot of these cases. And so being able to link that directly, I think is still one of the problems facing us.
I think, Simon, you've talked about attribution type issues.
Yeah, and also extreme events. I mean, it's, as Ali says, it's difficult to necessarily separate the extreme events over land from the ocean. I'm thinking particularly of tropical cyclones or hurricanes. A lot of our research, or some research I've been involved with, led by a PhD student here, she found that the ocean, the amount of heat you have in the ocean at the start of a hurricane season is extremely important for the strength of that hurricane season to follow. So you can see the temperatures becoming more extreme in the tropics. So that's not sort of a hazard you worry about, but it does then fuel hazards that you do worry about, such as hurricane landfall, particularly in Central America, where people are very poorly prepared for that, and in the US where there's huge economic damage as well.
So in terms of just thinking about hurricanes a bit more, is the thinking that there's more of them, or they're stronger, or what's the expected effect?
Yeah, it's difficult. So this is why I didn't say something like that, because it's actually really difficult to determine whether there is an increase in strength or an increase in number. That's one of the sort of unresolved questions, I think. But we expect the system to change. Hurricanes are fueled by evaporation from the ocean. That evaporation is controlled by how warm the ocean is, and the ocean is getting warmer. So you've got the potential to supply more heat to these hurricanes.
So if the ocean's getting warm, presumably that warming is heading further north latitudinally, so there's a latitudinal gradient in temperature roughly, isn't there?
Yes, and that's an interesting thing in its own right. So, well, this is quite a complex thing, I suppose. But if you look at the equator is warm, the tropics are warm, and the poles are cold, and that temperature gradient actually drives the jet stream to some extent when the heat's released at higher latitudes. Now, because we're warming the Arctic more, that temperature difference between the tropics and the poles has decreased, and some scientists are saying that has an influence on the jet stream and makes it slower. And once you have that happening, it can get stuck in particular positions, and you get storms battering the UK, for example, in severe winters. So again, there's a link between the large-scale properties of the ocean and local weather, not just for the UK, but other places around the world.
So we're in the UN Decade of the Ocean at the moment. How do you think that's going to help us? What's going on there? You know about that? I think, Adrian, you've been involved in this a bit.
Yes. So I'm involved in one program focused on the twilight zone, so the water between 100 and 1,000 meters. And I think that the value of the decade is that it is giving a major incentive to countries, institutes to work together, in the sense that I think that it's understandable and common that projects tend to get focused on a specific question. They want to go to a particular location, address a particular question. But I think given the problems facing us, particularly in understanding the role of the ocean in terms of the climate, we really need a consorted international effort. And I think the real benefit of the decade is that it is strongly encouraging people to come together. So to say the program that I'm involved in is all about coordinating activity in terms of how marine life is helping to store carbon in the ocean. But, there are other Ocean Decade programs in terms of acidification, oxygen, all of which are just trying to align the research so that they can actually make significant progress at a global scale over the course of the decade.
So are you guys involved in that at all?
I'm not currently involved in any of the programs, but I was originally involved in one of the reviews for the implementation plan for the UN Decade of the Ocean. One of the things that I think is most important about it is that I think kind of socially, we haven't given as much importance to the role of the ocean and the climate system as we should. And I think the UN Decade of the Ocean is really bringing that to the forefront and giving it a platform and visibility.
So we've talked mainly about ocean physics and biology, but obviously there are impacts on human beings. So in terms of what you're working on, where do you see the impacts of these changes on people around the planet, and where do you think the most significant impacts will be?
Well, there are many impacts. I mean, thinking about sea level rise is the obvious one, and low-lying countries, particularly bordering the Indian Ocean, for example, like Bangladesh, you can impact the people there in many ways. So you can impact them obviously by sea level rise directly, just eating away at the land, but also salinification of freshwater deltas, which changes the ecology there. I have colleagues working on that. So there's a huge exposure of a lot of people. Again, coming back to that recent IPCC report, I think that the statistic is about 3.5 billion people worldwide are at direct risk from climate change. And those are often in the poorest communities, the ones who are going to suffer the most.
Anything you'd like to add to that?
Yeah, I mean, I think following on from what Simon was saying earlier about the polar regions, and maybe as a nice example of how the ocean connects all of these things together, there's some modelling work that suggests that the changes in the ocean chemistry and the circulation that are going to arise are going to reduce the amount of nutrients coming out of the Southern Ocean. So, the Southern Ocean is a critical exporter of nutrients. And their predictions suggest that even though these changes are happening in the Southern Ocean, it may actually have an effect and drastically reduce the fisheries in the subtropics. So you have this remote influence in the polar regions, which is actually causing a crash in fisheries, which obviously has direct impact on people's livelihood in the subtropics and tropics.
Just to build on some of what Simon said, which is, and looking at the sea level rise and the floods and the drought, I mean, we have estimates, and the extreme events I talked about earlier, we have estimates of what the cost is in terms of human lives and just financially. And so we know what this is and how it directly impacts human society. But it's not just, and this is also linking into something we talked about earlier, which is is the warming of the events, are they increasing in intensity or frequency? It's also, how are they shifting? So there's regions that previously never might have had to think about flooding or excess precipitation. And all of a sudden we see these massive shifts in the low pressure systems to places that they've never even gone to before. So it's all these different tiers of things that we hadn't considered about how the climate system might change. And that's all directly impacting our society right now.
Peter, have we got some online questions?
We have, yeah. First question, what causes ocean heat waves?
It's all linked to, there should be a straightforward answer. So there's a lot that's still not known about marine heat waves. It's very much linked to background low frequency warming, but there's also oscillations in the system. So for example, Simon talked before about these temperature gradients between the poles and the tropics. And so you can imagine something kind of similar to that, in a season, in a year, or interannually, you have a lot of oscillations in temperature in the system. And sometimes these can be more extreme, anomalously warm. And so then we're linking, those extremes are directly linked, I say directly, we're still figuring this out, are linked to this background warming.
From the audience.
Yeah, so this is kind of a bit into Simon as well as Adrian. So you mentioned how models are quite important now to predict future climates, and that's all based off our observations now and kind of putting that into play. So what are the main maybe observations missing or parameters missing in these models to help better them predict current and future climate? Is it, for example, a biological or ecological perspective? Adrian were to mention that the food chains, there's still a lot missing from there. So what are the main kind of parameters you think still need to come into place these models?
Do you want to go first?
You go first
No,
on
thank you.
ecology, and then I'll come back to physics in a minute.
Yeah, I could give you a shopping list of the things that we don't know. I think the recent IPCC report highlighted with, I think it was high confidence, that impacts on the biology of the ocean were going to have a feedback on the climate, but huge uncertainty over what those were going to be in terms of magnitude of indeed size. So it just sort of highlights how little is known. Just to give you an example of sort of where our ignorance starts, just knowing what fraction of the organic carbon survives from sort of sinking past, say, 100 meters and getting to 1,000 meters, we still don't know. And without knowing that, it's actually very difficult to run a model without getting huge uncertainties. You can run a model with different estimates for that simple number, that ratio, and you get very different estimates in terms of the role of carbon in the ocean. And that's just starting with the small stuff.
And I think to follow that, I'll come back to the deep ocean again. And I heard a quite inspirational talk a few weeks ago at actually the first conference I've been to for more than 2 years, and a medal recipient, Celine Herzog. And she was talking about the need for deep ocean observations and the fact we have extremely few deep observations. And she had a map showing this great coverage of the ocean above 2,000 meters that we have as a result of the Arlo program, as a result of these floats, and virtually nothing below 2,000 meters. You see ship lines there from ships which have done surveys over the last 30 years. We really don't know how the heat is getting into the deep oceans. We've got very sketchy knowledge of that. So I would, if I had a large amount of money, I'd be putting it in to really observing the deep ocean, getting that picture. And hopefully that will come over in the decade ahead. But more's always welcome.
Just thinking about the heat in the deep ocean, my understanding is the deep ocean moves, things happen a lot slower in the deep ocean. So why is it so critical if it's not doing anything very fast, so to speak?
Yeah, because it's a reservoir, so you can put a lot of heat into the deep ocean, and it can stay there. But eventually, it will come back. I mean, we talk about climate change as if we're going to reach some sort of end state in 50 years or 100 years. We want to know what the temperature is then. But you go beyond that because eventually that heat comes back to the atmosphere on the timescale of several hundred years. So there's another problem lurking down the line. So that's one of the reasons we need to know it. But I think in the shorter term, we just need to see where the heat's going in. We think it's going in the Southern Ocean, a lot of it there, but that's based on a very few number of observations. We don't really know what other deep regions of the ocean are doing in terms of heat uptake.
Another question from the audience.
Hi. I assume when we run ocean models into the future, we run them several times to see the variability. What's the sort of range of possible futures we see, and what the best and worst case scenarios, and what the time scales are?
No, you're first this time.
It's not my area of research, but I was involved, so I've not been involved directly in the most recent IPCC report, but I was a lead author on the previous one. I'm quite fairly familiar with the current one. So if you're looking at the possible range of things that's going to happen in the future, that depends primarily on how much carbon we emit, how much CO2 goes into the atmosphere. And you can see, you can actually do a plot of amount of carbon going into the atmosphere and temperature, and it's a fairly straight line. So what we get, whether we get 1.5 degrees, unlikely, 2 degrees or 3 degrees, it will depend on what governments do in terms of the carbon limitation in the decades ahead. I think most models are saying now that if we carry on as we are, that would be really terrible. If we carry on with the mitigation processes that we have now, with the efforts to reduce carbon dioxide, which we're doing now, and we don't implement anything new, just carry on with what we're doing, we will end up with 3 degrees by the end of the century, which is a terrible number. If we carry on with the reductions we've got and put more in place, we might be able to keep it to 2.5 degrees. To keep it at 1.5 degrees would require a massive effort in the years ahead, which is perhaps not on the table at present. Well, let's speak honestly, it's not on the table at present. That's my take on it.
Yeah. Anybody else want to add to that?
Yeah, I mean, the only thing I can add, I think Simon's covered sort of the climate prediction well. Just from the marine biogeochemistry perspective, from the physics, most physics models look the same in that they've got mostly the same equations in, and it's down to subtleties. If you take apart a marine biogeochemical model, you will find it's entirely different because people have their own ideas on which of the dominant processes, and each of those is represented in a different way. So one of the major problems in terms of climate modeling, including the effect of marine life, is that we're still a long way from a consensus on what the important parts of marine life are.
Just to follow up on the modelling thing, one of the things I'm aware of is obviously the ice sheets are really important. And as I understand it, many of the climate models don't really include the ice sheets and their behaviour very well. Is that correct?
Well, I can't comment with expertise on that because I'm not an ice sheet modeler. But what I do know is there's a lot of research going on to just what effect intrusion of warm ocean water beneath the sea ice does to these land-fast ice sheets. So you can actually get situations where, depending on the amount of water which is coming in, and depending on the amount of melting, you can get further ingress of the waters and destabilization of ice shelves, etc. So that's something which is really hard to represent in the model, given that we have very few observations in the first place. So that troubles me a lot as to if you think about the uncertainties into the future. You worry about the overturning circulation potentially slowing down, but I would also worry about what's happening at the poles and whether large parts of the Antarctic ice sheet could suddenly melt and end up in the sea, which would lead to a very big sea level rise.
You got another question from the audience?
Yeah, question. So you talked a little bit earlier about ship-side methods and going to sea, and that's not going to go away. But in the context of future climate change, there's a bit of a catch-22 with the carbon footprint that you do when you do go to sea and how much a ship takes up. So what are your thoughts on like the future of observation to be able to do it sustainably while still getting what we need?
That's a great question and a very hot topic at the moment, as we have a lot of conversation towards net zero. I can't comment on any expertise on the engineering side of it, but most of what I can say is just that it's something that's being looked at right now. And there's a lot of people working on it, both from the sort of how can we reduce our impact from the ship and from the instruments that we use. And yeah, it's a conversation everyone's having right now and moving towards that. And the autonomous vehicles do help a lot towards that. Yeah, I mean, there has been a great deal of thought put into this. So within this building, the Marine Facilities Group, the Net Zero Ocean Capability project has been going on to try and identify things like this. And so some of it, as Ali says, is about
thinking about where we can bring in robotic systems rather than ship systems where possible. But also there are things like, whether you can reduce the fuel use by the vessels that we have, because at least for the time being, we do need to keep those vessels. And so there are things like, do you always need to have, there's something called dynamic positioning, which allows you to keep a ship in a very specific location. It's more fuel intensive than just having it sitting there. And so there are questions about just educating to some extent the scientists in terms of thinking about what they want to do with the ships. Whether you need to go to the other side of the Atlantic or whether you can do it nearer at home, just as a way of trying to reduce that usage.
Yeah. Have we got another question?
Question from the viewers online. What can individuals do to further prevent climate change?
I think that's coming up in the following panel, actually. Most people know what we need to do, which is to cut down on our energy usage, to make use where we can at home of renewable energy, for example, by switching supply, by cutting down on travel. It's those sort of things. We can all do that at an individual level.
And the other side of that is, think about this one a lot. I mean, we're a capitalist society. A large part of the economy is household consumerism. And the consumerism that we have right now is completely unsustainable and very linked to climate change. We think that as individuals, we don't have this power and that it's down to the government to make all these policy changes. But actually, we have an enormous amount of power and we can become more conscious about what we do in our everyday lives. Boycott fast fashion, reduce plastics, emissions, all these things. It's really everyday choices that can make a big difference if we all do them.
I think you can also influence companies and organizations by writing to them and saying. So I have an example from a friend of mine who's a primary school teacher who the children were doing collages about plastics in the ocean and they realized that Pritt sticks they were using were plastic. So they decided they would write to Mr. Pritt and say, look, we love using your Pritt sticks, but they're plastic. What are you going to do about it, basically? And they got a letter back saying, yes, we're thinking about how we can become more environmentally friendly. And that's not a climate change problem, but it illustrates that even a bunch of school children at 8 years old can have an influence on companies. Companies take notice of these things, so you can influence what's going on by writing to companies. So have we got any more questions from the audience?
Yeah, I have a question. And I guess the answer will be very dependent on what you're looking at. So each one of you might have a different answer to this question. But you're talking about how we need more observations of the ocean. And some of the observations we were talking about was long-term monitoring of it, while others you talk about expanding the locations where we are monitoring, especially in the Southern Ocean. So in an ideal world, we'd be able to do both now, but obviously that's not the case. So if you guys could prioritize long-term monitoring or observing more locations, which do you think you would do?
Oh, you're at the end.
I go. That's a very hard question to answer. I mean, it depends on resource available. Time series, so when you have a long-term observation, you have that valuable time series. I'd be loath to stop, some of the key long-term observations, thinking of the rapid array, so it measures the ocean circulation in the subtropical Atlantic, at 26 north, and that's been in the water now for 15 years or so, or 17 years. So I think the question is not so much about stopping that activity, but asking how we can do that in a more cost-effective manner. I know that there have been big efforts to do that by saying which parts of the mooring array can we take out. So in some ways, I'd say I'd want to actually reduce the cost of the existing time series without stopping them and make that resource available to some of these new observations we need in other locations.
I'll come clean. I'm not an observationist, so I think Aldi's probably better, more authoritative on this subject.
I can't do one or the other, and the reason is that, well, for me, I'm interested in large-scale circulation from observations as well as models. And one of the things is it's not just understanding how things are going over time; it's also how they're connected at different points in the ocean. So it's really hard to sacrifice one for the other. Either way, you're going to be missing something really important. So it's a bit of a cop-out. We need both.
Okay, right. I'm afraid we've run out of time. I'm very grateful to the audience and those people online who asked questions. So thank you. Thank you for coming to listen to us. I'd like to thank our panel for being so good at answering the questions. Thank you very much indeed.